Hi, Tony and fellow Physics180A members. We're Team Spicy Tofu, and we decided to do our experiment in an aquatic setting. Allie's going to explain why.
We decided to do it at the pool because me and Steven are lifeguards, and everybody jumps off the diving board like, a couple times a day. And we never thought about each. And we didn't know that there was physics behind it, so we decided to do the problem.
And underneath it.
Inside joke, inside joke. I'll be like, okay, this is Team Spicy Tofu, part of Team Spicy Tofu. Oh, he's not really part of our team. That's Jason. He's a helper.
A volunteer.
A volunteer. And this is Allie. And here, this is.
Are you still?
Hold it.
Are you
this
still?
Is Steven. And what?
You're recording.
Yeah.
Oh.
And the rest of our team is at home still, so because it's kind of cold out here.
That's not a problem.
But you're going off the diving board, so it's like...
Yeah, but it's still going in.
Okay.
What am I measuring?
We're going to measure the entire length of the board from the entire length, front to end, and then the length from where Jason's going to be jumping off to the fulcrum. And then...
Entire length and then...
Jason, real quick, what do you weigh?
Like 180.
Okay, 180. We'll use 180 and convert that to kilograms. I'm on top of things here.
60-something kilos.
Yeah, it's like 770. But okay.
What?
Okay, so 180 kilograms, or I mean 180 pounds. We'll convert that later. Force going down. Okay, so measure away.
I'm gonna hold that on the end.
Now he is...
Alright. Exactly 16 feet.
16 feet long is the board. And then to the fulcrum. Move in.
10 feet 4 inches.
And the fulcrum is 10 feet 4 inches. Do we have to measure the height? Or no?
Yeah, height to the water. Yeah, 3 feet 4 inches, height to the water. And,
So you have to convert all this to metric?
How do I stop recording? How do I stop recording?
Take it again. Alright, that was good.
Jump off in here?
Yeah. Perfect. I'd like to thank our volunteer, Jason.
Okay.
Alright, thank you very much. I owe you a Jamba Juice and a burrito. Alright. Alright, I just got N2, the force at N2, and I'm trying to figure out the force at N1. But do I need to make mg negative for his weight? Because at N1, it's negative because it's being, applied down.
Right.
But N2, the board actually lifts up in the back.
Going up.
You remember how he was talking about pivots at the N2? Yeah, and it's going up. So do I make a mg negative or positive?
Which way is the torque going? Is it going counterclockwise?
No, clockwise.
Which way is the moment arm going? Right, the moment arm is going clockwise, so then it would be negative.
Yeah.
Oh, okay. Makes sense.
Because the board lifts up. Because the
The
pivot point.
direct force should be going down, and then
So it should be opposite? I think so.
the normal force at the fulcrum should be going up. The other one should be...
Oh. That makes sense.
Yeah, it should be going down because it's sitting on top of it.
We have a diving board. You know what? You got it right there.
Yeah, it should be going down.
So you're saying that if this is our diving board and the N2, this pivot point, is going down like this, that the bolt on the back one is going to be...
down.
Oh,
Down.
that makes sense. All right.
Yeah, because that's what you have to do with your thumb right there. Look at that.
It works.
To begin, we're going to explain this diagram, and here's Crystal. Hello, we decided to do our project of a man jumping off of a diving board. It never occurred to us how much work actually went into the diving board itself and the forces that actually added onto it. We have the weight of the man acted on by N2, which is the force of the pylon, and you also have normal force on the back of it, which is the pivot point. That's about it.
So to understand how we arrived at this diagram, I'll explain a little bit. In rotational motion, the reason it's caused is because there's a translation between these 2 points. See, normally if a guy was standing here on the end of a board and there was a pylon here, there would just be an up and down normal force and force applied. But because it's all the way over here, it wants to set the board into a clockwise spin. So that's where this guy comes in and holds it down. That's why that force is down, this force is up, and the man's force weight is obviously down.
Here's our conversions. Our diver, Jason, weighs 180 pounds. That converts to 82 kilograms. And the diving board measured from here to here, all the whole thing,
Yes.
is 16 feet, and that converts to 5 meters total.
Come on. Alright, so here's our problem, and we use the sum of the torque in order to, right now we're looking for N2, looking for this one, we're looking for N1, not N2. And so we plug in sum of the torque is equal to negative mg times the distance. It's going to be this guy, this little dude on the board, times the distance away from the pivot point. And pivot point, we're using N1 right here. So it's going to be the whole board, 5 meters. And N2, distance from N2 to N1 is going to be the 2 meters. And so we plug that in, use algebra, and we end up coming up with 205 newtons for the force right here. And it's positive, so it's going to be going up. And we do the same thing for N1. In order to find N1, we just change the pivot point here to N2. So we're changing the pivot point to this one now. That way we can eliminate that, and now we plug in all the distances for N1. So the little guy on the board, distance from N2 is going to be 3 meters. Then distance from N1 to N2 is the 2 meters, and we eliminate that. And we end up coming up with negative 123 newtons, and that's negative, so it's going to be going down. And this makes sense because the guy jumping on the board is applying a force downward, and this is going to be the reaction force pushing up from this little stump here, from the fulcrum, and on the end here the screw is going to be holding the board down, so it's pulling it down. We're done.
That's not me in it. This is how I study.
This is how we work together.
What's next?
I think that's it. Here's the problem. Oh, you guys want me to get the stool?
Oh, yes, turn my phone back on, Bobby.
Here's our whole problem worked out here. Some of the torques.
What else do we need to do? Are you scanning it?
Yeah, I'm scanning it. Then that's for N2, and this one's for N1. And that's the answer. That's the answer. There's our picture.
Ew.
We are spicy tofu, not spicy tuna. Okay. Good?
Good.
Alright, so what does this mean about diving boards, Bobby?
Well, to me, I got to look at this.
Critical
right
thought with Bobby.
The man, we calculated to weigh 40.5 newtons. So that's obviously, there's an imbalance here because these are the resultant forces that we calculated by getting the rotational motion. So there's got to be some sort of potential energy and elasticity in the board. Of course, we know common sense tells us, but that's actually what lifts the guy up into the air.
Oh, that makes sense too. Yeah, it's got to be more in order to lift him. Otherwise, he'd just be sinking on the board and he wouldn't be moving.
Right.
Okay.
Exactly. So now I know how diving boards and things like that work.
And that's a wrap.